I will notice your questions there, or Phil will notice them. And between the two of us, we'll make sure that everything is answered for you. We also have all kinds of wonderful people here from JP3. So anything for some reason that Phil isn't able to answer, we've got a whole team on for you guys. So ask those questions, please. Just to make sure everybody sees everything that they should. Right now on the left-hand side of your screen, my friends, you should see a beautiful slide. That's the welcome presentation slide that's on your left. And then on the right, either me talking at you or everybody in a kind of series of names or grids of pictures. For the presentation, it's usually pretty ideal to have the speaker on your right. So that'll be Phil. And then on the left, the presentation that's going on. If you don't see that, or if you have any questions, guys, please let me know. My name is Chelsea Dalzell. I am moderating this event with the amazing people at JP3 and also Mr. Phil Harris. I'm probably going to go ahead and start my little welcome bit for what we're all doing here today and who the presenter is today. So welcome everyone to JP3's second global webinar. This one is focusing on chemometrics and data analysis. Today, we want to take the magic out of chemometrics and put the science into real-time measurement. Your speaker today is Mr. Phil Harris. So Phil is the president of Insight Analytical Solutions. He's a Calgary-based integrator, distributor, and developer of process analyzer and sampling technology, and he's a JP3 partner. Hence why we're all in this party together. Phil is a Bachelor of Science in Physics, Masters of Science in Chemistry, 35 years experience starting in the nuclear industry and coming to Alberta to develop process analyzer solutions for the oil and gas industry in '93 with Western Research. He's a fellow of the ISA, recipient of a Lifetime Achievement Award for Technical Innovation, the ISA Award for Excellence in Technical Presentation, a 7-time recipient of the GTFK Award for Best Technical Paper. He's the author of over 30 technical and research papers and travels internationally to teach courses on the design of process analyzer sampling systems. Without further ado, welcome Mr. Harris to the floor, please.
Thank you, Ms. Dalzell. Yeah, thanks, Chelsea. Chelsea's team has been instrumental in helping to set all this stuff up. She does a great job of, all the marketing emails that you probably saw, the obviously the moderating, and just making sure this all works. It's kind of the backbone behind all this thing is Chelsea Dalzell Creative. So appreciate that very much. Thanks for showing up, everybody. God, there's a lot of people on here I know. Just quickly look through some names. Dirk, I have not seen or spoken to Dirk Horst for an awful long time. Dirk, nice to see you. Let's see who else is there. There's Halton, Eretz, Jeff Burden, you're Phillips, right? You worked with Landis for a while, I think. Henrik, you're retired now from Valero. Nice to see you as well. All the JP3 guys here. We got Greg, we got Coyd, we got Nate, we got JZ, we've got, who else I see come on? John Stearns on there. Mohit's on here. So again, I got huge amounts of backup and support on the JP3 side. If we really want to talk about chemometrics, I think I saw Brian Rohrbeck walk by in the room here someplace. And of course, one of the people that knows the subject better than anyone and is going to be a fellow presenter at the ISA Analysis Division thing next week as well. So good to see you, Brian. Who else should I probably be saying hi to? I saw Rich Webb. I saw Elaine's on here up from Red Deer with Scotty. So yeah, welcome everybody. Thanks for coming. Okay, so let's talk a little bit about what we're going to talk about today. We're going to talk about near infrared spectroscopy a little bit. We're going to talk about chemometrics. And first, let's talk a little bit about the players who are involved here. So of course, I have to always get started, and that means I have to get things to work. So there we go. So it's kind of a little bit of a joint venture-ish thing, if you like. We run a website with Chelsea called Making Measurements Matter that is basically is laid out to do a bunch of webinars and provide educational solutions, whether it's online training, in-person training, webinars like this one. And so you got some bunch of emails that came in from Making Measurements Matter. In this case, we're focusing right on the JP3 technology. And so JP3 is an equipment and information company that develops and sells online analyzers, data analytics, and primarily, of course, the big product of theirs is this near infrared spectrometer we're going to talk about. And we work with them as a, hi, Jennifer. We work with them as a business partner and as their distributor up in Canada. So we're going to talk a little bit about the spectroscopy side, because I think it's important to understand what's different about the JP3 technology and the type of spectrometer they use and how it's implemented. And then we're going to talk about chemometrics and what we can do with it. And we're going to run through, certainly if you are an experienced chemometrician, actually, Chelsea, maybe let's put up that first poll.
All right, sounds good. 1 second, everybody. Oh, sorry, we still have people joining us, so I'm having to.
Oh, you're multitasking. Do you need Scotty to be a co-host as well?
Now I'm good, and yes, I will.
Yeah.
How experienced are you with the use of chemometrics?
Yeah, that one.
Yeah, let's do it. There we go.
So just to get an idea of the background of everybody that's here, kind of might be helpful a bit. Wow, what a great group. We're actually all answering the poll really quick too. That's cool.
We're almost at everybody.
Yeah, cool. Let's share that and then we'll
good enough for now. Okay.
Share, yeah.
All right, everybody.
So this is kind of interesting. So I'm grateful for everybody for putting this information in. I mean, because you see that there's not an awful lot of people that are really experienced with chemometrics. It's kind of a, not so much, I wouldn't say necessarily a new field, but certainly one that for a lot of us in the analyzer business, we tend to focus a lot on hardware and how things work and things like that. But a lot of the math that goes on behind it is not as commonly studied a subject. And so that's, kind of, if you notice some of the marketing things that Chelsea was doing, she was saying things like, we had these things about demystifying, taking the magic out of chemometrics, right? Demystifying the chemometricians. And so that's hopefully what the things we're going to try to do today. And like I say, there's some people on here that if we want to get into the real technical details, there's people on here who can certainly do those probably better than I can. But we're going to try to come at this from an approach to try to get you an idea of how chemometrics really fits and what we can do with it. So first, we're going to talk a little bit about near-infrared spectroscopy. And there's a reason why we want to look at near-infrared spectroscopy when we're talking about doing hydrocarbon analysis. When we look, it was really cool, actually. We just did some samples here in the lab. And we had a client bring in some diluted bitumen. So if anybody's familiar with, what they talk about in Canada, the tar sands or the oil sands, this is stuff that looks, when it comes out of the ground, it's like asphalt. And when we got the samples in the lab, they are jet black. You look at them and you think there's no way you can get a beam of light through these things. And the interesting thing about hydrocarbons like that is they're black because they absorb all the visible light. And so when we look at those samples, we go, oh my God, there's no way you're getting light through that. But as we move into the infrared regions of the spectrum, the transmission gets higher and higher. They let through more and more light. And in fact, there's places where they are virtually transparent to infrared light. And then we get out to about here, around 1600 nanometers. And suddenly all these hydrocarbons start to absorb light again. But they absorb that light with different shapes and patterns. And it's those shapes and patterns that then let us be able to do a qualitative analysis, if you like, what hydrocarbons are there, and a quantitative analysis, how much of them is there. So it allows us to both identify them and also to quantify how much of them are there. Now, this has been around for a long time. I mean, infrared spectroscopy, people started to realize that you could do things in the infrared a long time ago. Around 1900, there was a lot of tests that were done by Koblenz, who basically said, hey, every hydrocarbon has a slightly different spectrum. I can use this to identify hydrocarbons. Around the 50s, we started to pull it out to process measurements. Later, we started to couple with fiber optics. Some unique things have changed along the way, though, and JP3 has implemented a couple of those. One of them is to improve how the spectroscopy gets done. So a lot of times when we think about infrared spectroscopy, we think about diode arrays and dispersive devices, or we think about things like Fourier transform devices, FTNIRs, and all great instruments. Almost all of them have had a certain set of issues when used in the field. Either moving parts, difficult to keep perfectly aligned, differences from one instrument to the next to not be able to get precise wavelengths and calibration transfers, or long-term maintenance issues. So one of the things that JP3 has implemented, I know it's Timothy's on here from Axon. One of the things that JP has implemented is, if you like, just a way better spectrometer. Axon had developed this broadly tunable laser spectroscopy for other applications, one of them being looking inside people's eyeballs, optical coherence tomography, medical applications. So the JP3 took this technology, the core technology of that, and said, great, now let's take this and implement it and use it in hydrocarbon measurement. Gave them a long mean time to be between failures, really bright light sources. So again, now we can see through these dark crudes. And every spectrometer comes out with an internal wavelength calibration that makes it so you can really transfer models very well from one spectrometer to the next. Another thing that they implemented was this idea of taking the measurement out closer to the process pipe. It's still an extractive system, but we take a sample, we close couple a flow cell, and use that closed coupled flow cell to make a measurement right close to the process pipe. What it means is we can keep these lines short. So we have short transport lines. You know, when we look at analyzer sample systems, everybody says, you want to keep your samples lines short, because get faster response. We can use this device to make measurements at line temperatures and line pressures. So it means if we do all of our measurements under the same physical conditions of processes, we shouldn't get any phase changes. So now we don't have to worry about, well, I took my sample of natural gas liquids, but in bringing it over to the analyzer, it all started to bubble and foam. That's not good for us. We don't want that to happen. So we look for some source of differential pressure. It could be an orifice plate. Could be a valve. I can't write in red down there, I guess. If I write with red on red, it just doesn't work. Color works like that. So it could be a control valve. Anything that gives us some different pumps, anything that gives us some differential pressure, and that allows us to flow a sample out from the process through this flow cell and back into the process again. So that lets the sampling be. So we already talked about having a better spectrometer. Now we talk about a bit better way of sampling. The other thing is these flow cells are large-ish diameters. So, you know, everything on this whole thing is run in half-inch tubing or pipe. I'll put it as 2. So we got large diameters. So one of the big issues we have when we put conventional technologies in is that things plug off really easy. If I put in a chromatograph and I've got 1/8 inch and 16th inch tubing, plugs on me. Now I run everything in half-inch tubing and pipe through this flow cell that doesn't have much of a flow obstruction. Things don't plug off very easily. The other advantage is this laser goes down fiber optics really well. So I can take this part where the spectrometer is and where I like to refer to as the brain is. I can take this part that's going to do all the work of measuring and put it in a safe area, like something like an MCC building or a control room, and then use fiber optics to send a beam of light out from the brain through the flow cell, bring it back to the brain again on fiber. So no fluids flowing back to where this guy is. All the fluid stays in the process. No recovery tanks, nothing like that. We now send that beam of light over the fiber, bring it back. We measure that infrared light to get to a spectrum that we see. And we take that infrared light that we just measured, run it through some data analysis algorithms. This is the part we're going to talk about that later or today is how do we get to this part of it? We run it through these algorithms to take that measured spectra, that raw data, convert it into information. From the information, convert that into knowledge about what's going on in the process, and then use the analyzer to make intelligent choices, help us make intelligent choices, wisdom. And you can see why I mentioned those words, because they're going to come up in another slide yet.
Hey, excuse me, Phil.
Mm-hmm.
There's a question. Did you see the question in the chat already?
I did not.
Okay, so and Greg's jumped in, but
Yeah,
always, this is from Dirk Horse.
Mm-hmm.
Always taking the sample from the center of the process line?
Not necessarily. Not necessarily. We usually put a probe, depending on the size of the line we're going off of. You know, we follow kind of the typical best practices, kind of Horst. You know, whether it's you know, a third of the way into the line. On some really big, if we're on a really big diameter one, we may not even go a third of the way in because, of course, resonance type calculation stuff. But yeah.
Greg, yeah, that's what Greg said. Greg said recommend a third in most cases.
Yeah. But if we're on really small lines, if we've already got a bypass line or a fast loop, you know, if there's already a fast loop there that's a 1-inch line or something like that, then we'll often just sample right off the wall off of a T. Although some of our clients even put inertial probes in their fast loops, not inertial probes, isokinetic probes. So yeah, and that's another piece of this whole thing. When you're doing something like water and crude, or if you've got crude that you want to get the full sampling, you know, then we'll talk about isokinetic sampling and things like that as well. One of the other cool things about this technology is that the brain can handle more than one sets of fiber. So we could be using this over here, and we could be saying, I'm going to measure natural gas condensate. Oops, I'm in red, sorry. So I might be measuring natural gas condensate, a C5 plus stream over here, a liquid. And I can take that and run a second set of fibers out to this flow cell and come back and be measuring something completely different. This may be a crude oil. It may be natural gas. I may be doing a BTU analysis of natural gas. So a completely different measurement done at each measurement point that I connect the fibers to. And typically the standard unit, the CTX, we're able to do 4 different sample points. With the CTX-E, we can do 8 different sample points. So it makes our installation start to look a lot simpler. So this is a typical installation on a crude oil blending skid. See the big gray pipes down there with the blue control valve in it? We've got crude oil flowing through there. We're taking a small slipstream of that up to the 2 white boxes. You can see black things coming in on either side. Those are the fiber optics. In between there is the flow cell. So the sample is flowing through that 1/2-inch tubing, some of it going a little bypass loop around, some of it going right through the cell. Shoot the infrared beam of light through it. Beside it is a single stream JP3 analyzer and SSL, and it's making a continuous measurement of vapor pressure. So these guys want to know, what's the vapor pressure of my sample? How much butane can I blend into my crude and still hit the vapor pressure specs? So the one up here is being used for butane blending into crude. When we install these, again, if we're Canada, JP3 in the US, oftentimes we'll put these outside or just under a 3-sided enclosure. In Canada, of course, a lot of our design specs say we have to be suitable for a minus 45 degrees C ambient. And so we tend to put these inside of a little enclosure, a little box, put that same panel like you see there inside of a little box, mount that out right near the process. So, with this next slide just shows, this next slide that's not coming. There we go. I think it just takes a little while. There we go. So this shows an installation of a condensate stabilizer in Canada. Cold outside, have this heated enclosure. You can see the heater sitting down here. The same flow cell, same sort of flow paths. We're running a sample of natural gas condensate through there, mounted out in the field, back over here in an MCC building. So they didn't have to build, MCC. They didn't have to build a dedicated analyzer shelter. We put the analyzer back in the MCC building, run the fibers. You can see fibers going out. Oh, sorry, going out through the top over here. Let me just zoom that guy. Oh, it's kind of the internals of the analyzer, if you like. spectrometer at the bottom, single board computer to do all the number crunching, PLC for some controls around it, data communications hardware. So better spectrometer, optimizing our kind of our flow paths to get good response times, good capabilities to do the measurement right out of the process. And then we add in this next piece that we wanted. Processing the data. We have the advantages that computers have gotten a lot better, a lot smarter, a lot faster, and we've developed a lot better and smarter algorithms to analyze this kind of data. And, we look at a lot of our devices from cell phones, they do voice recognition, face recognition. All of that is really a type of pattern analysis, if you like. And so we take that same sort of technology and we apply it to chemical data. We want to take the spectroscopy, put some number crunching around it, the chemometrics, and create that into information. Actually go even beyond creating it for information. So I'm going to use the analogy here. There's an expression used in some industries, DIKW. We take data, we want to convert it into information. We want to use that information to create knowledge. And when we have the knowledge, we can actually start making intelligent decisions and refer to that as wisdom. So I kind of paraphrase an old T.S. Eliot poem, Choruses from the Rock. And so, we say, if we just look at data, where do we lose the information? Where is the information we've lost in all this data that we get? Where is the knowledge that we've lost by just looking at those bits of information instead of processing them and making them into more actionable things? And where is the wisdom and the ability to impact and control and change things that we've lost if we only look at the knowledge? So that's kind of the way I've looked at T.S. Eliot's quote there. Before we get into kind of the deeper parts of chemometrics, let's look at this from a fairly simple perspective. First, what do we mean by data? Data is anything, a collection of numbers, a collection of symbols, a collection of words in an unorganized form. Somebody puts a whole bunch of words on a piece of paper, there's data there. We can organize them though into sentences and maybe a poem or something like that. So we can take data and we can organize it. So in this case, I'm going to show some XY data. Let's just assume, for instance, I'm just going to change my pen color. Let's just assume, for instance, that this is some analyzer reading. It outputs some number. Unscaled. I mean, really, if you think about it, we get 4 to 20 milliamp outputs. We get, maybe this is a voltage output. This is lab results. As the analyzers have been reading, we've taken samples, we sent them to the lab, and maybe this is API gravity. We have all this unorganized data. It really doesn't tell us anything. So now we want to make it into information. We go, well, is there any relationship between these things? And so we put it all into a graph. And now we look at them and go, hey, there's a pretty strong correlation, it looks like, between these things. When I graph this stuff, I have more information. I can see information on this. I know there's a correlation. I can go further than that, though. I can take that correlation, I can do a least squares fit to it, and create this one simple equation right here. So where I have knowledge now. I now know that if my analyzer is reading any number, like let's say it's reading 1.0, I take that 1.0, I multiply it by 30.8, and I add 16.3 to it, and that's telling me what the API gravity is. This is knowledge I could pass on to somebody else. Whatever that analyzer is reading right now, this is how you make it into figuring out what your API gravity is. So I've gone from data to information to knowledge. And the interesting thing is, you see, I took a lot of data and I reduced it down to a little bit of knowledge. And not only that, with that knowledge now, if I know that for me to have on-spec product, it has to be less than 65. And I get an analyzer reading someplace out here, I can put that result up there and say, well, if the analyzer is reading over 2, I'm off spec for my product, so I should shut myself in, or I should put that to a storage tank. So I took this raw data like this, made it into information by putting it onto a graph, organizing it, analyzed that organized information to get my knowledge, and now I use that knowledge to make decisions that are going to make my life better. Maybe I sell better product, I make more money, whatever. An example of this might be something like transmix in a pipeline. When we're flowing fluids down a pipeline, it might be we flow heavy sour oil for a while and then light sweet for a while. And if it's Canada, we often put a bit of condensate in between those so that we can separate the batches. But we want to know what product we have. So even if it's a refined products pipeline, in this case, we say we're flowing premium gasoline, we're flowing regular, we're maybe flowing jet fuel, we're maybe flowing low sulfur diesel. We can have different products moving down this pipeline. As they move down the pipeline, the interface doesn't stay perfect. The interface mixes. So in between, if I flow premium gasoline and then start to flow conventional, in between there, this stuff is neither product. It's not appropriate to be sold as premium. It's not appropriate to be sold as conventional. It's something that I want to put away and reprocess. So what we'll do in a pipeline like that is try to identify the period of time that this transmix is happening. And if it's product A, the product, let's say it's flowing in from the pipeline, I put it into the product A tank. If it's product B, I put it into the product B tank. And if it's the transmix stuff, I put it into my slop tank. And that stuff I have to reprocess or I have to sell as a low value product because it's not on spec for anything. So the way this is done a lot of times is people would just look and they'd say, well, I know it takes about 2 hours. They change something at the refinery. It's about 2 hours to get to my facility. So when they switch products, 2 hours later, I'm going to start putting stuff in the slop tank. And I'll do that for the next half an hour because that's what I think my transmix time is. Oftentimes, this meant that they put too much material to transmix. If the product was good enough to be sold as premium, we could have put it to the premium tank. If it was good enough to be sold as conventional, we could have put it to the conventional tank. If it was actual on spec for jet, we could put it to the jet tank. And if we put it to that transmix tank, we have to maybe ship it, reprocess it, sell it as off-spec product. So we want to minimize that. We want to understand that interface better. I know it's Jeff's on here, and I think Jeff's a Phillips 66 guy. Phillips 66 and JP3 have been doing some of this work and made a press release middle of last year that using this technology, they're able to optimize that transmix and reduce the amount of time that they spend putting stuff to the transmix tank and instead put more material into their proper tanks. So you win two ways. You win because if you were going to put it to transmix and reprocess it, now you put it to the diesel tank. You got more diesel you can sell. And if you were going to put it to the transmix tank, the faster you fill that up, the more reprocessing you have to do. So there's a lot of economic value in doing this. So we want to talk about this application because when we look at how chemometrics can be used to separate gasoline and diesel, it's fairly, I shouldn't say it's simple, but it's a easily understood kind of process that's going to go on, or hope it's easily understood. I hope I've tried to put this in a way that's easily understood. What we show here is the infrared spectrum for diesel and the infrared spectrum for gasoline. And with the naked eye, we're pretty good pattern processors and image processors. With the naked eye, we can look and certainly say, boy, if that's what all diesel looked like and that's what all gasoline looked like, I could look at this and just see the difference. So this is what we want to be able to do, is tell the difference between these two products. And more importantly, tell the difference between these products when they're not necessarily perfect, but they're close enough to be able to still be sold as that product. So we want to know, sure, maybe my diesel I want to know when I'm on all of the specifications for diesel, or I'm on all of the specifications for gasoline. And so we can start to think about how we do that when there's a mixture there too. So if we take a look at those two spectra, we overlap those spectra. We see the physical difference, and we could do the first simple thing we could do is just subtract the two and say, what's the difference between these two spectra? And you see when we do that, we kind of highlight, I think I subtracted the gasoline from the diesel here. And so we kind of highlight that gasoline has this big peak over here. So if it's diesel, you have less of that peak. And diesel has some more peaks over on this side. So if it's diesel, you have bigger peaks over here. So I can look at any spectrum and say, how much does diesel look like? How much does it look like the diesel spectrum? And the parts that don't look like the diesel spectrum, how much do they look like that difference piece? And I can start to try to categorize my spectra as, does it look like diesel? Does it have diesel information in it? Or does it have some other kind of information in it? So you'll hear people talk about a thing called principal components analysis when they do chemometrics. And what that means is taking these hundreds and hundreds or thousands and thousands of spectra and saying, well, if I wanted to just, so that's all this data. If I wanted to just capture the information in that, how can I reduce that data space? How can I say, hey, it really fits into, a few, 2 or 3 or 4 or 5 different kind of shapes that if I add them together, I can fit everything. I can make a spectrum for everything that way. And we can apply principal components analysis to any place where we have large data sets. What it does is it tries to take these large data sets, like these big sets of spectra, and map it onto a smaller space. Is it diesel or is it gasoline? What's its API gravity? What's its vapor pressure? We want to take this big set of data, 850 points that we've measured hundreds and thousands of times, and compress it down into a smaller space. So I found a really interesting paper on the internet. The internet's a beautiful thing. This guy used principal components analysis, and he looked at world-class soccer players. And he said, I left some ink on here. There we go. So I'm going to take all these world-class soccer players, and I'm going to look at the skills that they have. And so he looked at skills like, their age, their ability to accelerate, their agility, their able to dribble the ball, their free kick accuracy, their ability to jump. I think heading's in here someplace. It should be heading accuracy. Took these world-class soccer players from all over the world, looked at all of their 35 different skills, and also looked at, there's kind of 4 positions on the field. There's goalies, there's guys who play midfield, there's guys who play forward, and there's guys who play defense. And he said, now if I start to look at kind of all of that data, find out which skills point as vectors towards certain groups, I can try to start to characterize these guys. So you can see, goalies are kind of like drummers. Everybody else in the band's always really cool, and there's this guy that drools and hits the drums. So goalies are kind of like that. Goalies are these guys out here. They stand out from all these other soccer players. They have a completely different set of skills. And there's a certain set of vectors, unfortunately, that all overlap in this thing. You can't see, but there's a certain set of skills. And they go, you have those skills, you fit over on the goalie piece. We look at skills like strength, aggression, heading, all these, those point to all the guys who are defense. And so he did this principal components analysis to see where different skills mapped out in terms of the player types and player positions. He did a second player where he compared a Brazilian soccer team to a Japanese soccer team, which was kind of interesting too. The point I'm trying to make here is what we're going to use principal components analysis for is to take really large data sets, 35 skills, 30,000 players, that's 35,000 data points, and reduce it down into pieces of information hey, if I need to find a good defenseman, I'm going to look at certain sets of skills. So the problem when we have real world data, and you can kind of see it here, there's a lot of scatter. When we have real world data, there's often lots of scatter and variability. When you're doing spectroscopy, there may be baseline shifts, there may be dirt in there, there may be wax in there, there may be additives sometimes, so things can change on us. So we start to do a bunch of things when we talk about chemometrics. You'll often hear people start talking about a word pre-processing. Before we get to this whole analysis of stuff, we want to make the data cleaner and pull out more information or make information appear more obvious to us. So one of the things, sorry.
Excuse me, Phil.
Yeah.
Maybe ask a question about what about interfering components that are not in the database?
Yeah, well, certainly that's the whole thing when you're trying to, it's one of the reasons why we want to end up getting to, I define these as, the skills are like physical properties, API, gravity, vapor pressure. The thousands of players are the thousands of spectra, and the positions might be different products. But if you didn't get, if one of these positions, let's say, you only had a few defense guys in there, you wouldn't build a good model which predicted how defense people do things because there's not enough data on that material in the database. So one of the things that happens with these inferential analyzers where we have to build models around it is we want to make sure that we've taken enough samples for the different products that are likely to go by. The good news is these types of models can usually give you a statistical predictor of how well they're fitting. So the model's running and it says, hey, this is diesel with an API gravity of 38.3. And I think I'm guessing really good right now. I'm on my A game here. And then when a different product goes by, assuming if we go back to Koblenz, it says all the different hydrocarbons have different shapes to their infrared spectra. And now the spectra comes in that goes, that doesn't fit the shapes of all the things I've seen before. The model might say, this is diesel with an API gravity of 41, but I don't think I did a very good job of analyzing this. So we get a statistical feedback from these sorts of models that is kind of a quality. If you think about fitting a straight line, you get an R squared number, right? And you go, this is how good my curve fit was. We get that same sort of statistical stuff when we're modeling these. So we can sometimes predict bad results, but we often know we're predicting bad results.
Other question, what accuracy can you achieve and how good can you determine the difference between the gasoline or the diesel or whatever?
Yeah, I'm going to bring up a slide to show that, but certainly it all depends on the application, but we do a lot of things like we'll do, say, vapor pressure of condensate. Now, one of the big applications in Canada is doing vapor pressure of natural gas condensates. And we end up, when the model has been built, we typically get into, we're the same kind of, because we build the model around the lab method, ASTM 6377, we end up predicting close to the reproducibility, repeatability numbers of ASTM 6377. So we just did a test where we built a model and then we took 12 samples over the space of about a month and sent them to the lab and compared. And we were within, if I remember the number, about 2.5 kPa. So, and the ASTM method says repeatability of 2.3 kPa, reproducibility of 4.2 kPa. So, we're right in that same as the lab accuracy kind of range on things like that. The tough part is when you're trying to do trace concentrations. That's a harder part. But when you're doing bulk physical properties, bulk components, a lot easier with infrared spectroscopy. Low concentrations, you don't get much absorbance, and that's where your errors will be higher typically.
So the accuracy depends on the let's say the model.
Yes. Yeah. How well have I built my model? How good was the lab I used? If I had a poor lab doing all my lab analysis, I'm going to build my model on the lab results. So again, you know, we look at saying we got to use a reputable lab, calibrated equipment, et cetera, et cetera, et cetera. So we'll do an additional piece typically on this data processing where we talk about normalizing the spectra, getting the area the same, mean centering them. And we start to get, it's not that obvious, I suppose, on this slide. All of these things are done to remove any biases and baseline, pull out kind of low frequency information that might be drift type stuff, and amplify and identify kind of the higher information, higher frequency patterns that show up in some of these things. So if you look up here, I'll start here, you know, red's diesel, green's gasoline, and blue is a product that's kind of in between the two, the transmix stuff. And you can see they kind of all sit and overlap on each other. By the time we've done all this data processing, you can see that the diesel corresponds to a projection onto the principal component, or a projection. Brian's going to beat me up, I know. He's going to tell me all the words I used wrong. It's a projection onto this eigenvector where the diesel says that thing's all going to be big, pointing up. You can see diesel has fingers that point up compared to this eigenvector. Gasoline has fingers that point down compared to this eigenvector. And when we have this transmix stuff, the fingers all kind of move around. So when one finger gets cut off over here, the other one shows up. And so we can look at any spectrum that comes along and see how it projects against these kind of patterns or shapes. So, you know, here we've shown it with just 2 spectra, 3 spectra. But when we start to put hundreds and thousands of spectra in there, there's this, we get all these different shaped envelopes. The ones that are red, you can kind of see there's a few red peaks up here. Those are telling us that was when the product was actually diesel. Down here, there's a few green peaks. That's the product when the product was actually gasoline. And the blue stuff is all the stuff that was happening when it was neither of those. So again, so now what we've done, so again, I want to think about what the process that we're going on here. In that much earlier slide, we took some data and we fit it to a straight line. We only had 2 variables, X and Y. Now we have 850 variables, absorbance at every wavelength. We want to find out the projection onto each of those, how important those are, and are they correlated to differences in the product? And in this case, they are. So if we were actually running this on a pipeline, what we would see is, I'm going to zoom this piece of this. Well, first I'll draw it. Down here, there is a projection that corresponds to diesel. Oops. Down here, oops, I'm supposed to be green. Sorry, it's the other green. Down here, there's a projection that corresponds to gasoline. This is how much of that principal component, how much of that shape was in the spectrum. And in between there, there's all this blue stuff. That's the stuff that's not properly either product. So we can use this now and say, the analyzer is projecting onto the principal components over here, it's gasoline. If it's projecting onto the principal component space over here, it's diesel. And once it moves out of a certain range of those, it's one of those other 2 products. Or it's not either one of those products, it's a mixture. So another way we can look at it is over time. So down here we have time. We can look at the projection onto those principal components. How much of that shape is in the data I'm seeing? And we see that if it's got a positive amount of that shape in there, and that positive amount is up around 10, we know it's diesel. And we can say in this window, if as long as it's running within this window, I'm diesel. So we can do a qualitative analysis here. I'm running in this window, I'm diesel. I'm running in this window down here, I'm gasoline. And if I'm not in either of those 2 windows, I should be putting this stuff to my transmix tank. So I can use my principal components analysis. How much do you project on this vector to say which product is it? Kind of a qualitative type thing. But I can also take how much it projects onto that principal component. Just like I did before. Now I can use that as an X and Y thing. Just like, remember, I did that plot with the X and the Y. How much of X value do I have there, this principal component? And what did the lab tell me the API gravity was? I can make a mapping between those. So now that I've got this principal component information, I can do qualitative stuff like what product is it? And if it's and I can also do things like what's its API gravity? What's its research octane number? What's its vapor pressure? Depending on what products it is. So the whole reason, again, going back to this, the reason we want to do principal components analysis is we want to take these great big data sets, reduce them down to the smallest set of vectors or shapes that we could say, I can predict everything in this data set with this group of shapes, and then use that group of shapes to say, from those things that give me information about the products that's there, I can project that onto a physical property I want to know, or I can project that onto how much butane is in this thing. And so JP3 in their online systems has some nice software to be able to visualize that. You know, we end up with this process map, kind of like a heat map that sort of shows, hey, I've got a whole bunch of data over here on this product. I got a whole bunch of data over here on this product. And there's a little bit of stuff that happens in the middle. That's my transmix part. And you can see the transmix happening on this upper chart. I have to go back and I got to move something around if I want to be able to see. Oh, sorry. I guess I can look at it here. Oh, no, I don't have the right colors. Anyways, in this particular case, you know, they're looking at a product and they're doing an analysis based on those principal components, saying, what's its API gravity? What's its read vapor pressure? Final boiling point, octane numbers, run them on. What's flash point? And so they build models once we've taken the data sets, huge data sets, lots of data points, lots of huge data sets, correlate them to lab values, build the models, figure out the principal components, do what's called a principal component rejection, predict these products. So the point of all of this, again, take all this data, begin reducing it down into a space that lets me get to from data to information to knowledge, and then I have the wisdom to know I changed products right here in the middle. And stuff in between there, when that slopey line's there, it's going into the slop tank. When it's flat on either side, I can actually sell that as product. So again, the reason we focus on transmix is, in this case, we only have a couple of things we're trying to predict. And we can see the obvious difference well between gasoline and diesel. When we do this on more complex products like natural gas condensates, and we're doing a full C5 or C12 plus analysis, you don't see a lot of difference when you just look at the spectra. You know, the nice thing with this application is you can physically see that there are differences in the spectra, and what the analyzer is doing, what we're using principal components analysis to do in pre-processing is to amplify those differences, figure out a way to model them, correlate those models to things we really want to know, use that to make a wise decision over what we should do with this product. So when we look at this thing, when we look at this transmix optimization side of things, you know, when we have a refined fuels pipeline, or, you know, if you're looking in Canada, you look at what comes out of Suncor, what goes on the TMX line, Trans Mountain. You know, it'll go from being crudes and condensate, or crude oil, heavy crude, bitumen, to condensate, to gasoline.
Phil, there's a question in the chat. Sorry to interrupt.
Okay. Yep.
So actually we've got, oh, there we go. And
I already answered it.
Okay, cool.
Nate, jump in there, buddy. Yeah.
Okay.
Cool. Cool. We're good? Okay.
I think we're good, yeah.
Okay. So we want to figure out that interface, and that interface, global losses to transmix interfaces, are expected to, or projected to be in the hundreds of millions of dollars a year. So optimizing those interfaces can be a way to print money without really having to change our operations a lot. We make the measurement, we just make better decisions of which valve to throw.
Phil,
You
do
know,
you
and so,
want to just pop it just really quickly so that everybody else knows what the question was, and
oh,
that,
sure.
so that it's also here for everyone.
Yeah.
The question was, can this be applied to gas analysis?
Yeah. Okay.
So
Yeah. So JP3 has done a lot of work on the natural gas side in the US, especially. In Canada, most of our installations have been on the liquid side, but gas, just because gas prices here were so low for a long time. Now people are starting to worry a little bit more about what's happening on the natural gas side. Everybody here was trying to produce natural gas liquids, and making natural gas was a problem because we didn't have enough pipeline capacity. So now that we've seen the change in pricing, the gas side is becoming more interesting. How many lab samples and how long needs to be taken for the Chemometrics standard reference graph? Interesting. Again, good question. It's one that comes up a lot. And it depends, it's certainly application driven and how much variability there is in the product. But, you know, we'll typically see, and I'll let Nate jump in, if we're doing something like a vapor pressure model, we have a big thing up here for condensate pipelines, C4 minus model. I mean, we've done those now with 20, 30 samples, but we often, one of the other things that JP3 has, you know, this is why we talk about them being an analyzer company and a data company. They've got that data from hundreds of installations already. So when we go into a new application, we can say, well, what infrared spectrum are we seeing from this guy's natural gas condensate? Let's compare it with our library of all the natural gas condensates we've seen and use data from other facilities to build an initial model and start moving that model forward and build out models from there. So typically, it depends a bit on how many variables we're trying to measure and also how much variability there is in the product. But Nate, what would you say? Most models have 40, 50 samples in them by the time they're done?
Yeah, yes. Hi, I'm Nate Watson. I run Chemometrics for JP3. So all the team that does all the model building, they all work for me. And so the answer is it varies a lot because there's a lot of literature on this. One kind of set of rules of thumb that's usually most people could get at if they wanted to is ASTM 6122, which actually lists, if you're going to say that my model is in accordance with ASTM 6122, there's a lot of requirements you have to tie with. And basically, the more complex your model, the more samples you need. But like Phil said, we generally, because we are now sitting on that last count, we have like 30,000 calibration samples sitting in our library. And assuming that your product is something like other products we have seen, we have the ability to kind of tap into some of that data to help expand out the data set without needing to go out to your site and pull anywhere from 20 to 50 to 60 samples, depending on what your product is. You know, simple products like the sample that Phil just showed you of the diesel and the gasoline, you know, trying to predict API gravity on that set of data right there, you can see that we were able to get 881 dimensional data down to one dimension that basically covers all the differences between those gasolines and those diesel. So it's not a super complex system. Other cases, it's not that easy. So that was a lot of words, but hopefully that answered the question, as it varies a lot.
So interesting. So yeah, and so it's, again, you know, interestingly, so when we, JP3 is out of Austin, Texas. And so their initial installations were almost all in the southern US. And when we started bringing our first units up to Canada, or installing the first units up in Canada, we said, oh, we're going to do a natural gas condensate. Well, they started seeing the spectra and they're going, that's not condensate. It's not the condensate we see down in the States. The US had condensates way lighter than this. The other stuff looks more like crude. And so, you know, the first models we built up here for condensate took a long time and a lot of samples. And now as we've built up our library of Canadian installations, that modeling time, we were just talking about it within my group, just a few guys from my group here, Saul, Doug, Jason, are all Insight guys. We were talking about yesterday, like, man, we're getting these models done way faster, way less pain. And so, yeah. Do all analysis measurements comply with repeatability specified by the standards? So the standards typically define what measurement method was being used. So we can't really say, hey, we are equivalent to the repeatability method of such a standard in terms of any kind of anything that's in a standard. But when we build the model, we test it against those standards. And what we do is document performance against those standards. So we say, hey, if you're doing if your reference standard is ASTM 6377 for vapor pressure, do all your lab analysis versus that. We'll build our model to match your lab analysis. I don't know if that answers that clearly enough, Dirk.
Yeah,
So,
I think that's the right answer, because
yeah,
in principle, you focus on the type of sample and you build your model on that.
yeah. And so the way I look at it, Dirk, is if I was doing custody, if I'm going to do a custody transferred agreement between you and I, we'll probably pull a sample and send it to the lab.
Correct.
But if I want something, I can do process control to predict whether I'm going to sell Dirk some condensate, and he wants to know it has a vapor pressure less than 100. And I want something that can give me a data point every 15 seconds to tell me if I think I'm on spec. That's where the analyzer shines, process control. Custody transfer may still be done on lab samples and composite samples and all those sorts of things.
Correct, yeah.
This is more of a controls device, if you like. So like in the transmix thing, is I could just wait 2 hours and put it all into the transmix tank, but I'll lose money doing that. So I'd rather just make a measurement that says I can put it this way or this way and make my cuts properly.
We have another question in the chat. Phil, do you see that?
Yep. I mean, well, it depends. I guess it really depends. I mean, so on the liquid side, on liquids composition, you'll certainly see liquid inject net GCs, right, for doing chemical composition. This is one of the big applications that's coming up here. Oh, Brian, sorry to see you go. Give me a call sometime. We should chat.
So can you ask the question that Dirk?
Oh, sure, yeah.
So people know what you're talking about.
Yeah. Thank you, Chelsea. She keeps.
Have everybody's back up in here,
Yes, thanks. Types of analysis that we can, so the question was, what are the types of online analysis that we compete with? So we'll see, we've replaced a lot of chromatographs on difficult liquids applications, dirty condensates. When we talk about condensate up here, this is a natural gas condensate from a debutanizer. And you can see it's nice and clear. One of my service team ran his lawnmower on this. This is the natural gas condensate we see in a pipeline, or off the bottom of a condensate stabilizer. And this one you can run through a GC relatively easily. And this one, your sample conditioning system, has issues with the waxes, the clays, especially when you're looking at condensates that come from plant inlet. There's sand, there's clay, there's all sorts of things in there that make it difficult to get the sample into the analyzer. So one of the, early on, I said one of the things that was an advantage was how the measurement gets done, and using large bore tubing with big flow paths and not needing to filter a lot of stuff out, because the infrared sees dirt as just, there's something there scattering light. It changes my baseline. It doesn't affect my spectral shape that much. That's why we do all this pre-processing. Get rid of baselines and all the things we don't want to see. So chromatographs, online vapor pressure analyzers, viscosity, things like viscosity, raw and mon, a bunch of those physical property type things. Again, people might still use the traditional lab analyzer to be monitoring how their process is going on a periodic basis, but they go, this gives me my control signals. If you look at a refinery, they'll often have an infrared analyzer to do RVP of gasoline, and because it's fast, they can blend, and then they'll have other methods for saying, but I'll check it every once in a while against something else. Samples we get checked from the lab of end user. If it can't be done, what's the alternative? So we end up using a lot of a third-party lab, Venkat. We'll use Maxim, or in Canada, it's Maxim, Agate, a few other labs where we send the sample into them for the analysis. So with the analyzer, we tell it we're pulling the sample now, we send it out for analysis, and then we get the analysis back in a week, and we start adding that information into the model. So I'm running just a bit over, so I'm going to try to wrap this up pretty quickly because we have one other poll that I want to do because it's interesting. So when we look at places we can use this, we talked about transmix, but when we look at places we can use this, it's right across the hydrocarbon processing market space, if you like. Everything from upstream, right at production wells, if we want to look at quality at the well or do reinjections, to gas processing like gas plants and frac plants, condensate stabilizers, pipelines, tank storage, and what's coming in and out of tanks, and then making its way all the way down to the downstream side, and refineries. So, Chelsea, there's a poll in there, I think, called applications.
Yep. Oop, one sec. Okay, and it's launched.
Perfect. So what I'm just trying to get here is if you were considering the use of this sort of technology, what types of applications are probably of the most interest you? And I think, yeah, it's set up for multiple choice.
Did you want to cover that question? There's a question in the chat, Phil. Do you want to handle that while we're doing this poll, or wait?
How long did it take to performance the model based on your experience? Yeah, sure. I mean, again, it's going to vary a little bit on application. We're just doing a few installs right now in Canada, and typically it's been probably from pulling first sample to Nate. I think we're talking about validation on the next round of samples. This probably been about 2 months.
And again, that's highly variable, like we were talking about before. So, for example, we recently have done an install, which is a ethane into propane blending operation, and because there is no complexity to ethane or propane, they're pretty straightforward products. There's no isomerization. Ethane in Saudi Arabia looks like ethane in Canada, looks like ethane in Eastern Asia somewhere. Whereas crude oil is very different based on geography. So, if it's a very clear product that it's what it always is, we can pull samples right out of our library and you'll be calibrated from square one. But if it's crude oil, if we've never seen samples from that geography, we're going to have to start from scratch and it'll take a lot longer.
Yeah. Good. And again, it depends too a little bit if it's a property that we've modeled a lot of times, like vapor pressure, or a property that we're doing for the first time, right? So, yeah.
Yeah, this is Greg. I would just add, so what we've been working on and what we've been developing and we're now utilizing is, and again, I may get in trouble for calling it the wrong thing, but it's what we call global model sets. And so for applications that we've done a lot, where we've got a broad reference library, where we've developed lots of models and we have lots of experience, we can out of the chute basically load these model sets into the analyzer before we ever ship it. And so as soon as it's plugged in, as soon as it's commissioned, it will start producing, in many cases, quite useful data at that point. And then we may simply pull some samples to validate it or to fine tune it at that point. So again, it's application dependent. So it can be very minimal and it can be more extensive if it's a complex product or application that we haven't done before. So normally when we're talking about these, we always are looking at, so what's the application, what's the product, what's our experience, and then we can give you a much more specific time frame in terms of what kind of sampling and what kind of time frame would it take. And of course, all of that is part of the commissioning and installation package that we do. So it's all part of the kind of total package that comes along when you implement one of these systems. Thanks, Phil.
Yeah, thanks, Greg. I saw there's another question in about Nate's sour gas. Jay, I think you got the cutaway flow cell on your desk. Could you bring it by for me? Thanks, buddy.
Coming.
Yeah, thanks. So yeah, it is suitable for sour gas, all stainless steel construction, sapphire windows. I didn't go into that. I did talk about the flow cell a lot more in a previous presentation, which we have a link to up on YouTube as well. But it is 316 stainless steel, which is again a NACE compliant material, synthetic sapphire for the windows, not corroded by H2S at all. So yeah, certainly suitable for sour service. Thanks, buddy.
You're welcome.
Appreciate it.
Sorry, Phil.
Oh, right.
Guys, sorry, just so that everybody knows, he's got something in his hands. You can actually control how big Phil is on the right side. So there's just a little vertical toggle. If you want to drag that over to your left, you're going to be able to see what Phil's holding in his hands a lot easier.
Yeah.
Sorry, Phil, go ahead.
Yeah, no worries. Let me just see if I can zoom this. Oh, no, didn't do it. Okay, so this is the flow cell. So you see it's 316 stainless steel. It's this way. 1/2 inch port running in through the bottom. So flows, depending on whether it's gas or liquid, will change the direction of flow, but flow is going through the cell. Large diameter, so it doesn't plug off easily. Synthetic sapphire rods that are crystal clear, as you can see. But the advantage of sapphire is it transmits infrared light well. And it's also the second hardest thing next to diamond. So things like sand, clay, bitumens, etc., aren't going to damage the surfaces. So basically the only material that the fluid comes in contact with is 316 stainless and synthetic sapphire. We've tested these up to close to 15,000 pounds, have a Canadian CRN to around 1,500 pounds, 100 bar if you like. So high pressure, so we can run high pressure, high temperature fluids through it. There's another question in the chat. I'm just going to put up, maybe you can put up the poll results, Chelsea, while I'm answering this. Thank you.
You're welcome.
Principal difference between FTIR. Yeah, one of the big differences is FTIRs always have a moving part. So one of the problems can be, when you're in a situation like a blending skid and there's a lot of mechanical vibration, anything with moving parts tends to become unhappy over time. The nice thing with the JP3 spectrometer is this tuned laser doesn't have the moving parts aspect to it. So it's well suited for industrial type applications. One of the things when I talk about that usually is I say that, you'll see a lot of FTIRs in refinery because there's lots of instrument mechanics there. But if you're going to go to a blending skid in Fox Creek, Alberta, 9.5 hours north of Calgary, there's nobody up there going to be to maintain it. So you want to have something that has virtually no maintenance. One of the unique things, or one of the things about the JP3 device is it can be extremely low maintenance product. No moving parts, long mean time between failure on the light source. And we don't have to do the interferogram side of things. So with an FTIR, if you want more resolution, you end up increasing your noise usually by adding in more steps along the interferogram. And so whereas a JP3, we typically run it at quite high resolution, about 0.5 nanometer steps. But if we change the resolution, it just changes the scan time a little bit. So when we look at the products, it's interesting. So you can kind of see that pretty much all of these, every place where somebody wants hydrocarbons to be measured is some place where we say, well, we have applications for the technology. Interesting, a lot of it is in the analysis of natural gas, because of course I know, like, again, Dirk is probably one of the most competent people you're going to talk to about flow measurement and compositional analysis for natural gas compounds. And so, again, there's always that, everybody loves their chromatographs because they're accurate and they're reliable, or relatively reliable. But again, moving parts, injection valves, calibration stuff. And so interesting. Yeah, thanks for the feedback in here. It's always interesting for us to look at, where does the application interest come from, right? All right, just about done again. Sorry, I'm a little bit over. This probably needs another update. Over 600 measurement points. Greg, you probably have a better number. Installations all across the US and Canada, every basin. You can sort of see big hotspots down in the Permian, in the Bakken, up Canada, up in the Montney, the Haynesville, I think is the one in Louisiana. So yeah, lots of installations, gas applications, liquids applications, condensates, refined fuels. Been doing multiple installations since we brought it up to Canada now. We're in the process of just getting 3 or 4 of them up and running right now. And so with that, I'm going to wrap it up and just say, we'd be happy to talk to you about an application if you're interested in one. There's applications, we've got multiple applications already developed, more that we would love to do with you. And I'm going to give you a couple contact names right here at the end. Greg is out of the US offices, JP3 and Flowtech, and did an acquisition with JP3. So they're a Flowtech company right now. So Greg's out of the US office. I'm up here in Canada. Feel free to email us. You're going to get an email from
you.
I'll see you in the database. Yeah. From the rock star over there. You get an email from them, and with a copy of the presentation, we'll get you a link to the video of the presentation, like once it's all ready.
Phil,
yep.
I'd also like to say that I should have added it, but we have a business development director in the Middle East, based out of Dubai, and his name is Mohit Kul. He's on this call, and if anyone needs to get in touch with him, they can send anything to me and I will make sure he gets it, or you can just put MKOUL in front of the same at Flowtech IND that I've got, and he'll get that information as well. So I just wanted to make that clear for our international friends that have participated on this webinar, and thank them for joining, because I know it's a different time zone over there than what we have in Texas and Canada.
Right. See, we got a couple of questions in the chat too. Hey, Henrik. Model IP. So that's an interesting question. I might let the JP3 guys handle that. Typically right now, and again, this is one of the things that's been a bit different. When you were looking at FTIRs and refineries, oftentimes the refinery would have, or the oil company would have its own chemometricians, and they would build their own models. And one of the things that JP3 has brought to this is the idea that we'll put the spectrometer out there, we'll get the data, we'll organize the lab data, and we'll build your models for you. So, but I guess as far as the intellectual property of the model, I'm not even sure how to exactly answer that. So the data all belong, they answer that. Good.
Yeah, I'm not, in terms of JP3 retains rights to the sample database. So all the samples that we collect and pay for are stored in our database. So all of those are, but they're not really intellectual property. I mean, they are intellectual property, but they're just a bunch of numbers correlated for spectra. So I have a bunch of spectra and corresponding VPCR4 values for those spectra. So, but those aren't intellectual property as much as just data I have stored in a database. In terms of modeling, principal components analysis, partial least squares, all those things have been around for a long time. Even if there ever was a patent on them, it's expired. And I don't know that they're so open source that I don't think you could try to patent those if you wanted to.
Right.
So yeah, I hope that answers it. So JP3 has lots of patents, but it's mostly on hardware things, not on the actual database methods, because they're pretty general across a lot of industries and a lot of applications.
Yeah, along with that line, we're really not generating, let's say, new IP when we're implementing these systems. We're simply taking, tools and techniques and special equipment that we've developed and applying it to create a model set for local use. So I don't think if there was ever going to be any IP created, that would all be, I guess, sorted out up front, but that's usually not the case.
And while a lot of people don't know about things like partial least squares, it would be the equivalent of trying to patent a straight XY linear regression. Just you can't do that. It's kind of what is it? There's a word for it. It's kind of general knowledge for practitioners.
Paul, I didn't see you snuck in the room, but I see you asked a question as well. So yeah, Paul's asked about, do we need a pressurized gas cell for gas applications? Most of the gas applications that JP3 has been done under pressure. Certainly on, if it's sales type gas or a gas processing line that's at pressure, we prefer to do it as pressure because it puts more molecules into the optical path, get a better measurement. The lower the pressure, the longer the path length cell we have to use, basically.
I think that's it for the questions in the chat.
Yeah.
Anyone else have anything for Phil?
Phil, may I ask you a question? Yeah, I believe it was long ago in the past, but what was the reason to go into near-infrared instead of infrared range? As known, you can get the same information about hydrocarbons in the infrared range, especially for fundamental vibrations against overtones.
Right.
So from general point of view, I would say it's looking like infrared range is more promising. And still you made decision to go to near infrared.
So
what was the motivation? What was the main reason for that?
So especially because one of the things we were really interested was liquids analysis. So like crude oils, condensates, LPGs. The absorption bands in the mid-infrared are a lot stronger. And so you end up having to go to shorter and shorter path length cells. And now when you start thinking about, say, a natural gas condensate off of an inlet stabilizer or crude oil straight from a wellhead, it's dirty, it's got dirt, sand, clay, wax, asphaltenes, dead mice. There's all sorts of stuff in there. And so you don't want to have too short of an optical path because it'll plug off on you too easily. Or you have to do so much more sample conditioning.
And we're already in cases where we're using a 1 millimeter optical path and we're seeing less than 10% transmission.
Yeah. So if you took if you got almost another, this is why people use ATR cells in the mid-infrared.
Right. Yeah.
So you end up having to use ATR cells, and that has a whole set of issues associated. That's what I have an FTIR in the lab with an ATR cell if I want to do mid-infrared, but you end up wanting to have microns of path length, really.
Or alternatively, go to gas phase, heat this sample, and bring it to gas phase. And
that's the whole thing we wanted to avoid. If it's a liquid sample, we want to measure it as a liquid. So as you try to take a sample of condensate and make it into the gas phase, the heavy ends don't vaporize properly, and everything starts to plug off.
Sure. Yeah.
JP3 does not do a Raman right now, Paul. So far, there's another question in the chat. All right. Well, if there's nothing else, I think we will wrap this one up. But appreciate you all coming. It was great seeing a lot of you that I haven't seen for a long time, and always appreciate
very much. Thank you very much, Phil.
Yeah, thanks, Dirk. It was great seeing you.
Thank you.
I'm possibly coming over to. I'm hoping if we get to travel, I'm supposed to teach one of the Swaedrock courses over in Holland, and so I'll try to give you a shout out over there. Or are you not there now? Oh, you're on mute. Sorry, you muted yourself there, Dirk. I didn't hear the last part of that.
Well, I hope to meet you one day again here in Holland.
That'd be great.
Of course. Thank you very much.
Yeah, thank you. Thanks, everybody.
All right, thank you, everyone. And as mentioned, we'll make sure all those email addresses are very easy to find in the replay email that comes out. So we'll make sure that Greg is in there, Mohit.
Yeah.
Well,
and again, sorry.
Phil Harris and anyone else that would like their information shared.
Yeah, again, a big thanks to Chelsea and her team. They're the ones who, like I say, help organize all this and make this thing work. So my Doug's on here and he has a thing with GSD getting shit done. And their team gets stuff done for us. So it's great. That's what happens. So thanks, Chelsea.
Thank you.
Thank
Thank
you,
you, everyone.
Phil.
Thank you, JP3.
Thank you.
Thanks, everyone.
Yeah.
Take care.